Hi everybody. So today's lecture is definitely going to be a little different because we want to discuss something called the right-hand rule of magnetism. As you recall from previous lecture on magnetism and magnetic force, particularly the magnetic force on a moving charge, of course all magnetism results from moving electric charge, and so a charge in motion has a magnetic field. But when it enters another magnetic field, a force is created on that charge. Now force, being a vector, has both magnitude and direction. And we saw to get the magnitude, we simply used an equation. Force equals BQV, field times charge times velocity. But to get to the direction, that was the tricky part. Because where the velocity vector may be on one axis, say the x-axis, the magnetic field could be running along the y-axis. That makes the force point along a third-dimensional z-axis. And so that's the tricky part. When dealing with magnetic forces and fields and velocity vectors, it's a three-dimensional thing, not a two-dimensional thing. So it's very visual. So we'll see if we can actually show this in this video. But basically the idea behind the right-hand rule is given any two of the vectors to figure out the direction of the third. So for example, if you're given the direction of the velocity or current and the magnetic field, you could figure out the direction of the magnetic force. Or if you're given the vector direction of force and velocity, you could figure out the field direction. Or if you have force and field, you could figure out velocity. So to see what we mean as we go along. Now, how this works. Well, of course, first of all, it's called the right-hand rule because you need to use your right hand. Now, as I tell my students, basically you're going to hold your right hand in this orientation with your thumb sort of 90 degrees to your fingers and your palm very flat. Now you can turn your wrist any direction you want, but you have to keep how your thumb and fingers and hand all the same, okay? But you can move them around. Each part of your hand is going to represent something different. The way I like to describe it to my students, you have one thumb. And so whichever way your thumb points, that must be the same way that the charge velocity or the current is flowing. Okay, so if my charge was going up in the air, my thumb points up. If my charge was going down, it would point down. Okay, if it's going right or left, anything like that, it would point that way. And we'll talk about this third axis like this later. On your hand, you have many fingers, okay? And there's often, of course, not one magnetic field line, but many magnetic field lines. So I like to use the fingers to point in the direction of a magnetic field, okay? So whichever way the field is actually pointing, that's the way you point your fingers. Again, keeping your thumb however it's going to look. And then the other part, and this is different sometimes, teachers teach this different ways, but I like to say that with the palm of your hand, you're able to push things, okay? So whichever way you can push the palm of your hand, that's going to be the direction of magnetic force, whichever way you can actually push with the palm of your hand, okay? And that's what the right-hand rule. So we'll see how this sort of all comes together. Now, first of all, the right-hand rule applies only if you're dealing with positive charge or conventional current. There is technically a left-hand rule if you have negative charge or true current. But what I tell people to do is just learn the right-hand rule, and whatever answer you get for the right-hand rule, take the opposite if it's a negative charge. Yeah, I'll go over that again a little bit later. But for now, we'll just stick with positive charge. So the interesting thing is, first of all, is this three-dimensional effect, because we tend to do things on paper, which is really two-dimensional. And in dealing with vectors in two dimensions, it's pretty easy. If something is going up or down, well, we can show up or down arrows. Okay, so that's sort of in the y direction there. Okay? So you have sort of a positive y and a negative y direction. That's easy. Equally, if something is going right or left, okay, well, that would be, say, the positive x and negative x. That's easy to show. Okay? The problem is now the z-axis, okay, which either requires that you go into the page or out of the page. Okay? So the way to look at it is this. If you were to shoot an arrow into the paper, well, you would see the cross feathers going away from you. Okay, so we're going to use an X to represent the cross feathers of the arrow as if it's going into the page, away from you. It's nothing to do with you, it's the paper, into the page. Meanwhile, if an arrow was coming out of the page at your face, you would see the tip of the arrow, or a dot. So a dot represents something coming out of the page. Okay, so out of the page is the positive Z, into the page is the negative Z, sort of the way to look at it. So now let's look at this first example. Here I've got a charge, again with a positive charge, going up the page with a certain velocity, and a magnetic field that is going into the paper. Okay? So, with my right hand, well, first of all, my thumb is my velocity, so I want it pointing up into the air. Okay? Now, my field is going to point into the paper. Okay, so I've now got to turn it so it's pointing into that paper. Okay? And when I do that, I find that I have to push to the left. Okay, my palm will push to the left. What that means is that the magnetic force must act to the left. Okay, because my thumb is up, my field is pointing into the paper, and I push to the left. That's the direction of magnetic force. Let's look at the second example. In the second example, my velocity is coming out towards my face. Okay? Out towards my face. Okay? At the same time, so it's, if I'm doing this, I'm looking at my thumb. Okay, so you're looking at your thumb. And then my field is pointing to the left. Okay, so my fingers are pointing to the left. So with my thumb pointing to my face and my fingers pointing left, I see that I can push down. Okay, so the magnetic force must be down. That's the direction of the magnetic force. Starting to see it a little bit? Maybe not. It does take a lot of practice. Now, for my next one, okay, my velocity is pointed up. And at the same time, I'm having to push into the paper. So the missing thing here is actually my fingers, my magnetic field lines. My velocity says to go up, my force says to push in. Well, that gives the fact that my magnetic field lines are pointing to the right. Velocity's up, force is in, magnetic field lines are pointing right. So that's the direction of my magnetic field. My magnetic field lines point to the right. The last one, example here, the velocity is missing. We have force pointing to the left. Okay, we have magnetic field coming out at my face. Okay, force is to the left, and magnetic field is pointing out towards my face. So here's my right hand. Okay, I need to turn so that my magnetic field is pointing towards my face. So those fingers are pointed towards my face. Okay? But now I've got to rotate my hand, okay, so that my force is pushing to the left. So with my fingers pointed at my face and my hand with my force pushing left, I see that my thumb is pointing down. So down must be the direction of the charge velocity. Again, fingers are pointed out towards my face, force is pushing to the left, my thumb is acting down. So the charge velocity must be down. That's basically how that works. Okay, here's a look at a couple other examples. In my first one, my velocity is left while my field comes out. So the missing is the force, the palm of my hands. Okay? So first, let's start with my fingers, as I want those pointed out, okay, towards my face. And then I have to rotate my hand so that my velocity is pointed to the left. So with my fingers out to my face and my velocity pointed to the left, I clearly have to lift up with the palm of my hand. Okay, so my force must be up. In my next example, I have velocity and force, so I'm missing magnetic field lines. I'm missing my fingers. Okay? So in this case, my thumb has to be pointed in towards the page, okay, away from me, in towards the page, while my force has to be acting to the left. So with my thumb pointed into the page, away from my face, and my force pushing to the left, I see that my magnetic field lines, my fingers, point down. So the field must be acting down. My next example, I have field lines and force, so I'm missing velocity. I'm missing the thumb. Okay, so let's take a look at this one. So in this case, I start off with my magnetic field lines pointing to the right, and then I have to turn with my magnetic field lines pointing to the right and push down with a force going down. And so by doing that, I can clearly see that my velocity is pointed into the page, away from my face and into the page. So I would draw an X saying that my velocity is going into the page. Starting to see it now? Let's look at the next one. So here my velocity is pointing left with a force coming out. So again, I'm missing those magnetic field lines. So let's start off. I need to turn my velocity so it is pointed to the left, and then at the same time I need to come out towards my face. Okay, come out towards my face, out towards me, pushing out. And to do that, with the velocity pointing to the left and forcing out towards my face, I find that my magnetic field lines point down. So that's the direction of the magnetic field. And the last one, again, I'm missing force because I've got velocity and field. Okay, so here I want my velocity to point to the left, and then at the same time I want my magnetic field lines pointed into the page, away from my face and into the page. Okay, those arrows are going away, they're X's. And to do that, my thumb pointed left, my field lines pointed away from me into the page, I have to push down. So my magnetic force must be down. Okay? By the way, notice something interesting. In the first example, when velocity was left, that meant force could not be left or right. When field was out, that meant force could not be in or out, which means the only possible directions for force were up and down. You see, one vector has to be on each axis, x, y, and z. In the second one, velocity was in, so in or out's not an answer for B field. Force is left, so left or right couldn't be an answer for B field. So magnetic field could only be going up or down in that case. So that's also sort of a way to help you out, to at least get it down to a 50-50 shot. I highly recommend that you pause this point, go back, rewind, and try to do these again before I explain them. See if you can figure out the answers again before I explain them. It would be a really big help. Okay, so let's put it all together now. If a 5 nanocoulomb charge traveling up the page at a velocity of 2 times 10 to the 6 meters per second in a 0.4 Tesla outward magnetic field, it's pictured below. Determine the magnitude and direction of the magnetic force. Now the magnitude is just that equation. Magnetic force is B times Q times V, where we have a magnetic field strength of 0.4 Tesla, a charge of 5 nanocoulombs. Now remember, nano means 10 to the minus 9, nano minus 9, and a velocity of 2 times 10 to the 6th. And that gives you a magnetic force of 4 times 10 to the minus 3 newtons. That's the magnitude, the amount. Okay, well let's look at the direction. Now that's where my right-hand rule comes in. Okay. Now in this case it says my velocity points up, and then I have to turn my hand so that my field points out towards my face. I'm looking at my fingers. Okay. And when I do that, I find that I end up pushing to the right. Okay? Velocity's up, fingers out towards my face, pushing to the right. So the magnetic force direction is to the right, or if you want to say the positive x direction. And that's basically how that works. Now, like I said, if this was a negative charge, okay, well, the right-hand rule tells me the force would be to the right, but I would switch it and say it was left if it was a negative charge. That's the only thing you have to ever remember if you come across a negative charge, is it's the opposite answer of the right-hand rule. Practice and you will get it. All right, I'll see you next time.